Hello everyone, it's Mr. Davis with you back again this semester for the Chem 112 Lab video series. This semester we're going to be showing you a few things that you did not see in the 111 series. To begin with, we've got these neat little computers that are really just Raspberry Pi computers inside of a plastic case with a number of ports. These are called Vernier, that's the manufacturer, LabQuests, that's the model. And what they allow us to do is hook a number of different sensors, such as temperature, pressure, pH, and a whole lot more. So what they are is little monitoring devices, and I can actually record data over time and do a number of other things like that. But again, it's just a small little pocket computer, Raspberry Pi, inside of a plastic case. So we're going to be using this today for measurement of temperature with a temperature probe that looks like this. It's just basically a small metallic probe with a plastic handle. And we're also going to be measuring pressure. With that, we've got a pressure transducer. It's this little plastic box through a valve that goes to a tube, and it's going to go into our experimental apparatus, which for today is going to be an Erlenmeyer flask. The next thing we'll have today are a series of baths. Usually these are just water baths, but because we're going to go below 0 degrees C, I've actually got a chiller here, and I've got it set for minus 20 degrees C. And the way I can get away with doing below 0, because if it were water, it would freeze up and we'd have ice. That wouldn't do us any good, so what I've got is a mixture of 50-50 ethylene glycol and water in here. It's basically just a lab grade antifreeze to allow me to get below 0. So there's minus 20, and there's an ice bath, 0 degrees C, room temperature. That's a 20.3 degrees C right now is what I'm reading on my Vernier. And then I've got some heated baths. These are just electrically heated water baths. There's an electrical heating element at the bottom of this. And if I tip it up, you can see it's just a water bath. It's about 30 degrees C. There you go, 29.9 to 30 degrees Celsius. And finally, I've got another heated water bath showing 40 degrees Celsius. So for today's lab, we're going to examine and record the relationship between temperature and volume of a fixed quantity of gas at constant pressure. As far as the pressure is concerned, we're going to leave that constant, and to verify that, I'm going to use this gas pressure sensor hooked up to my apparatus so that I can make sure that my pressure is constant throughout the experiment. For temperature, we've got our different temperature baths, as I explained earlier, all the way from minus 20 up to 40 in the lab today. And for volume, I've got a simple Erlenmeyer flask. Note that there are no graduations on the flask. And the next step, I'm going to determine the volume of this Erlenmeyer with water. Finally, I've got a 60 milliliter syringe, and what will happen is as the volume of our gas expands or changes, increases with increasing temperature, it's going to push that plunger out, and it's going to change the overall system volume. And I can see right now, for example, that I have 20 milliliters of volume inside that syringe. So now for the next step, we have to determine the volume of our empty Erlenmeyer flask. Remember, it had no graduation, so what I'm going to do is I'm going to add water to this, and I'm going to remember that water, pure water, is 1 gram per cubic centimeter or milliliter. 1 gram per mil. Okay? So I'm going to pour water into here all the way up to the very top, and then I'm going to put the apparatus together the way I would have it set when we run our experiment. So there, that's all the way full. Now I'm going to add my stopper, and the excess water is going to come out this port right here, and that would be where our syringe would be, so that we can measure the difference in volume, our increasing volume as we increase temperature. So here we go. We put the stopper in, and a little bit's going to bleed around the sides and come out the top. I'm going to put the stopper in just like I would have my apparatus when it's ready to go. So that is full. So now I can just simply remove the stopper, and now I've got a tiered balance here. And remember, tare is 0. Just one more time, I'm going to 0 it. Make sure I get the 0. And now I'm going to add the water to the beaker. The number of grams, make sure I get it all. The number of grams of water will equal the volume in milliliters. So what I've got for this experiment, for the video portion, is I've got 131.444 milliliters of volume in my empty Erlenmeyer flask. Okay, so we're back at the apparatus. I've got my empty Erlenmeyer, my syringe with the plunger all the way down. And remember, the volume that we're going to be tracking will be the volume of the Erlenmeyer, which we calculated out before, plus the volume of the syringe as that plunger moves up and out. I've got the gas line coming over to my pressure sensor, and I've got a temperature probe. But I'm going to give a neat little demo here because you guys are going to do methane or propane in the simulation. So what I've got here is a little bit of butane lighter fluid. Okay, so the port, the way I've got this port set up is that this input line right here, this top one, is connected to the system and to my pressure sensor. So again, I've got my port open to the atmosphere, to the system and everything. Now, when I put this in here, it's going to take that liquid butane, which is inside this can. It's a very small amount, just a few grams, but it's under pressure and it is a liquid. I can hear it sloshing around in there, you know. So I'm going to put this here and we'll see what happens. We'll just give it about a 1 second squirt. Ready? I'm going to count 3, 2, 1, and I'm going to give it one more. 3, 2, 1. Boom. And as you can see in my Erlenmeyer, there's a little bit of butane that made it in there as a liquid. So we're going to go ahead and proceed. I'm going to charge this system with the gas, and then we'll record our volumes at different temperatures. So here's our data for our -20 bath. What we show is a -19.9 to -20, so we'll just call that -20 degrees Celsius and a pressure of 0 atmospheres. A quick note is that there is a pressure absolute and pressure gauge. A lot of times if we were to measure this in pounds per square inch, atmospheric pressure would be 14.7 psi or 1 atmosphere. So pressure gauge would be measured relative to that. So a 0 in gauge pressure would be equal to 1 atmosphere. So what I've done is basically zeroed out the pressure so that we could see relative to atmospheric pressure. So what we have is a 0 atmosphere in pressure and a minus 19.5. It's drifting a little bit, but at any rate, our volume is showing at exactly 3 milliliters. So what we've got for our volume in this experiment is the volume of the empty Erlenmeyer plus 3 milliliters. Okay, so I've moved the apparatus to the 0 degree C bath, and I'm getting a volume in the syringe of about 14.8 milliliters. And here's the data from the vernier. We're showing 0 degrees Celsius and 0 atmospheres for pressure gauge. Okay, my system is at equilibrium at room temperature. And I can see that because the pressure, the gauge pressure is close to zero. It's kind of drifting up and down. So I know that now that is just baseline noise, and it's showing a temperature of 17.1 degrees Celsius for the room temperature bath. My volume is about 25.5. Okay, so now we're in the 30 degrees Celsius bath, and as you can see, our new volume is about 24.5 milliliters in the syringe. We can see. And for our final bath, it's a 40 degrees C bath. We have a volume of 32 1/3, so I'll call that 32.33. Just a point to remember is that when you're doing your HM lab, you want to use the data that you derive from the HM simulations. Don't use this data. This video series is really just to show you what the apparatus looks like if you're in the real lab. In the HM simulations for experiment 2, step 2, the procedure calls for us to evacuate the flask. And what that means is to remove the air from within the flask. And we'll do that by pulling a vacuum, thus removing the air from our Erlenmeyer. There's a few ways we can achieve that. One of the most common of which is called a water aspirator. And all that is a simple water faucet, a cold water faucet with a side arm. And when I turn the faucet on, the rushing water accelerates through this jet and out. And because of the low pressure here at the T, it pulls air into the side arm. So therefore we have a vacuum being pulled by the water. So if I turn on the faucet, this side arm is pulling a vacuum. So I would just hook a piece of hose up to that vacuum. And again, the water rushing through here causes that low pressure to pull air in to the tube. So I get a vacuum on that. So for the operation of an aspirator, the colder the water and the higher the water pressure, the greater the flow, the greater the vacuum. So that's one way. Another way is we can use a mechanical vacuum pump. And this is just an oil mechanical pump to which I have a tube. And when I turn that on, it'll pull the vacuum this way. So I've got that attached to our system. And I'll go ahead and fire that up and show you that we've got just under 1 atmosphere. And the reason we're not at 1 atmosphere is we're above sea level here. So we've got about 0.98 atmospheres of pressure here. So when I turn on the vacuum pump here, it's pulling the air out of the apparatus. And when I open the valve, you'll see the pressure drop. So I'm going to pull back. And as you can see, it's got about 0.26 atmospheres of pressure. And the longer I let the pump run, the deeper the vacuum will go. In other words, the lower the pressure will go. So that's just a short explanation of the evacuation of the flask. Okay, so I've got our apparatus all set up so that we can simultaneously monitor the pressure inside of our Erlenmeyer flask and the mass. So this is a platform balance. The resolution isn't as good as what we might have with a smaller balance. In other words, I only get to the tenth of a gram. That's 100 milligrams, but it's good enough for this demonstration. With a 250 milliliter volume, we should see a several hundred milligram reduction in mass. That is the air inside of this flask. So the flask is a heavy wall, vacuum filtration flasks. It's a little heavier duty than our typical glassware, and this one's nice. It's also got a rubber coating on the outside just in case it were to break due to the vacuum. It would all be contained within that rubber that is around the outside of it. So we're looking at a starting pressure. Again, we're above sea level, so it's going to be a little less than 1 atmosphere, of 0.9805 or so atmospheres. So we'd record that, and our starting mass is 753.8 grams. Okay, so we've got our apparatus all set up, connected to the pressure transducer and the vernier, and the top port is going out to the vacuum pump. And so as I fire it up, we should see a quick reduction in the pressure, and also a several 100 milligram reduction in mass. Here we go. And right out of the gate, we're down to about 0.1 atmospheres. And I've lost about 300 milligrams so far. As we continue to pump this down, now I'm at 753.4 grams, so I've lost about 400 milligrams in mass. So there's my data for atmospheric pressure and reduced pressure. In this case, as I continue to pump down, it would take a while to get down much lower than 0.05 or so atmospheres due to the narrow diameter of the tubing, but for the demonstration purposes, this is just fine. It's less than 0.1 atmospheres at 0.0635 and reducing, and 400 milligram loss in mass.